In this second video on reactions of alkenes, we'll take a look at the problems that keep us from attaining or achieving regioselectivity. We've seen some of those already. We'll look at the addition of H2O to alkenes, appropriately named hydration, and the addition of protons, H2, to alkenes, hydrogenation. Clearly, regioselectivity is something to strive for, along with stereoselectivity. There's problems with attaining the right amount of regioselectivity, in other words, getting things to go where you want them to. And we saw already that you can have alternate products forming when you have different carbocations forming. And of course, you're relying on the favored carbocation to form, but that's not always the only product that results. We also have the possibility of rearrangements, and here we're going to focus on hydrogen migration, which is one type of rearrangement. You may also read in your book methyl group migration. We're going to hold off on that for now. So here's an example of a reaction of the type we've been studying. So the alkene initiates the reaction with bond forming there, bond breaking there, and we have our new bond to hydrogen there, resulting in a positive charge here. Now, of course, we could hope that perhaps our desired product is then produced by the addition of bromine to that plus charge, and then we get our bromine adding there. But that wouldn't be a very good educated guess as to what product we would attain. We might hope we get that, but more likely, once we reach this stage, you would have a hydrogen migration. So this hydrogen with its two electrons will sort of pogo stick over, hop over with its electrons, onto that plus charge. So we have our hydrogen now bonded there that used to be here. That's that hydrogen. And now that has left a plus charge here. Notice we've gone from a secondary carbocation to a more favored tertiary carbocation. So that's the driving force for this hydrogen migration. You would never have a migration of hydrogen to go from a tertiary carbocation to a secondary. You would almost always have it like this, going from a secondary to a more favored tertiary carbocation. Clearly then the bromine will now come and bond to that plus charge, forming that bond there, and giving the most likely favored or major product. So this is an issue of regio control, regioselectivity, additional complications arising from not just the formation of different carbocations in different places, but also the possibility of rearrangements. Toward the end of this module, we're going to see how organic chemists have overcome these issues, but they're going to involve more complex reagents. Back to some of the fundamentals again. Addition of water to alkenes is an important one. The net addition is the addition of OH and H across the double bond. First step is the same as what we've been studying. Acid conditions, right? So if you see a reaction where you have H2O and H2SO4, for example, common lab acid, you should assume that that is really producing hydronium ion as the reactive species, which is in fact the case. And that you're in a sea of water, essentially, way more water than anything else. Bond forming, bond breaking, we've already seen this reaction. New bond to hydrogen there. Water is produced from hydronium ion, or it's just floating around in that sea of water, like I said. Electrons forming a bond there to the plus charge, high electron density to low, forming that new bond. Our knowledge of formal charge allows us to reassess the formal charge at an oxygen there. Now we see that it's plus. Notice this oxygen is the same as the oxygen in hydronium ion with 3 bonds and a plus charge. More water can come over and help us complete the reaction by abstracting that proton there, breaking that bond there, and producing our alcohol. If you need to show the lone pairs to keep track of them throughout the process, you should do that for a while. Notice that the acid catalyst is regenerated. And recall the definition of a catalyst. It's not used up in the reaction. Now, of course, we have the other alternative, which is going to proceed along the same lines as what you see above here, with the formation of a secondary carbocation, not as favored as the tertiary carbocation above, but perhaps we get some of this. The sequence is all the same throughout, but notice we end up with, rather than an achiral product above, we end up introducing 2 chiral centers here, and so we already know that that's going to result in a mixture of RR, SS, I'll say SR, and RS, 4 different compounds, 2 pairs of enantiomers, and diastereomers of each other. So again, an issue of regio control, lack of regio control, I guess I should say. Continuing to keep stereochemistry in mind, really important. Notice how we're bringing in all our knowledge from the whole quarter, really. Here's an alkene reacting with acid, following the same procedure as above. We get our secondary carbocation. We cannot get a primary carbocation here because you can't get primary carbocations, remember? They're too unstable. Addition of water to that carbocation forms that bond. Loss of a proton. This latter step is just deprotonation. A pretty trivial step to get to the alcohol, and introduction of a chiral center, by the way, R and S. And the question is, all right, keeping stereochemistry in mind, do we have R, or do we have S, or do we have both? Well, that question's easily answered by looking at this stage right here, bracketed. So this is the point at which stereochemistry is introduced. Remember that carbocations are trigonal planar, and so I've drawn it down here, drawn this molecule down here with some perspective. Notice how flat it is, and the water molecule at this point has an equal likelihood of coming in and bonding from the top face or from the bottom face. So really you expect a 1-to-1 mixture of R and S enantiomers up here, and we call that, if you remember, a racemic mixture if it's equally 1-to-1 RS. So a mixture that's 60-40 R and R to S is not racemic. It's close, but it's not. Okay, so, but clearly understanding bonding and structure here helps us understand the resulting stereochemistry and predict it. Another fundamental reaction is the addition of hydrogen to alkenes. Hydrogenation. Pretty easy reaction to understand. You're adding a hydrogen to each carbon of the double bond. Clearly the double bond then goes away. The net reaction is shown here for an example. Here's our alkene. When you add hydrogen and the metal catalyst palladium or platinum, and hydrogen is a gas, in fact, in the reaction, notice the hydrogens come in and add on the same face of the alkene, cis addition, or sometimes called syn addition. If they were coming in opposite, it would be called anti-addition. So syn and anti. Fix that a little bit. This would be anti-addition. Or trans addition. Cis, trans, syn, anti, where the hydrogens are like this. However, you do not get this in this reaction. So here's the thing. You could memorize this fact that the hydrogens are adding syn, and that's useful. But to understand why they're adding syn, you need to understand the mechanism of the reaction. Shown in this figure, pretty good one from McMurray. We'll see similar ones in other books. So our metal catalyst here, so this is palladium or platinum. I think palladium's a little cheaper. You bubble hydrogen gas, H2, through the solution with that metal catalyst, and the hydrogens, notice, bind to the surface of the metal. Then the alkene comes in, binds also to the surface of the metal, and then, since there's so much hydrogen in there, picks up a hydrogen. So here, that carbon's going to pick up a hydrogen. Right there is a new bond to hydrogen. Partially reduced intermediate, notice it says. Then, in departing from the surface of the metal, the other carbon picks up the other hydrogen. And now you have an alkane resulting from what was an alkene. The fact that it's all taking place on the surface of this metal, you can see in this picture, explains why it's syn addition. So fundamentally, you can memorize reactions and pretty much understand or predict a net reaction much of the time, some of the time maybe. But if you don't understand the mechanisms, there's something missing there where you might have trouble predicting the product of a reaction. And certainly you would have trouble if you encounter a reaction that looks a little bit different than what you saw before, but really is the same mechanism. So, and the mechanisms rely on thorough understanding of structure and bonding, where implied atoms are, where lone pairs are, and where electrons often want to go.